All right, so now I'm going to present the algorithm for the bisection method. Okay, so it's going to have a bunch of inputs, which include the function, which you're trying to find the root of, f of x, the initial interval a and b, some tolerance, tol, and n, which is going to be essentially the maximum number of iterations, so that the method will always terminate even if it can't find the root after you've tried it for many times. And then the output is the sequence alpha n, and then the final number of iterations. So you first check that the interval which is given to you is guaranteed to contain a root, right? If it doesn't, the bisection method isn't guaranteed to work. So let's check this first. So if f of a times f of b is greater than or equal to 0, then you stop. It actually is equal to 0. That means one of them is already the root. So, but in any case, all right. So then you let the iteration count be 0, and we set a flag which I call mstop be 0. So, all right. So while n, oh, sorry, it's not which, while n is less than or equal to capital N and mstop is equal to 0, I do the following. So I iterate, increment the iteration number, n is equal to n plus 1. I look at the midpoint of the current interval, which is 1/2 a plus b. And then if 1/2 b minus a, which is sort of the absolute error, right, is less than the tolerance, and absolute value f at alpha n is less than the tolerance, right? So this is, again, this is the absolute error condition. This is a residual error condition, which we talked about before. Then if those are true, then mstop is equal to 1. So I'm flagging that if both conditions, both stopping criterion are satisfied, then I will flag to stop the iteration. Okay? All right. Then the next thing I need to do is I need to update the interval a to b so that it's an interval of half the length and it contains the midpoint. Okay? So I check if f of a times f of alpha n is less than 0, so that means the interval from a to alpha n is the one which contains the root, then okay, so then what happens is that a is equal to a, the left interval stays the same, but b becomes alpha n. So the new interval is a comma alpha n, right, which is what you want if f of a times f of alpha n is less than 0. Okay, else the other subinterval should be the one you have, so a becomes alpha n and b becomes b. All right, so that's basically it. Okay, so I can end this. All right, so I'm not really going to, I'm just going to end the while loop. Okay, and it's sort of understood that I'm just executing this if this condition is true, or this set if it's false. Okay, so that's really just the bisection method. It's very, very simple. It just checks again that the initial interval satisfies the condition that the function changes sign over that interval. And then if it does, it's like it checks whether you've maxed out the number of iterations or you satisfied the stopping criterion. And if you haven't, then it increments the number of iterations. It computes the midpoint. It checks the stopping criterion, which is whether the absolute error is small enough or the residual error is small enough. And if it is, then it flags to terminate. Otherwise, it will check which of the intervals, either a to alpha n or alpha n to b, contains the root, all right, and update the subinterval accordingly. Okay, and that's basically the bisection method. It's a relatively straightforward method. Okay, so let me just stop here for now.